Welcome to a deep dive into one of the most enigmatic chapters in Earth's history. We are traveling back roughly 720 million years to the Neo-Proterozoic era, specifically the Cryogenian Period. If you were to look at our planet from space during this time, you would not see the familiar blue marble we know today. You would see a brilliant, blinding white sphere. This was a time when the planet plunged into a deep freeze so severe that ice sheets may have stretched from the poles all the way to the equator. For decades, this has been known as the Snowball Earth hypothesis. The prevailing image was that of a dead, frozen world, encased in a shell of ice a kilometer thick, waiting for a volcanic super greenhouse to set it free. However, as scientific scrutiny of this frozen epoch has intensified, a competing, and perhaps refining, theory has emerged. It paints a picture, not of a sterile, solid ice ball, but of a dynamic, slushy world, where life clung to existence in open waters. This is the Slushball Earth hypothesis. Today, we are going to explore the geological and biological evidence that supports this model, the fierce debate it wages against the hard snowball model, and its profound implications for the evolution of complex life, including our own distant ancestors. To understand the Slushball hypothesis, we first have to appreciate the paradox it attempts to resolve. In the mid-20th century, geologists began finding telltale signs of glaciers, rocks known as tillites, dropstones, and varves, in places that paleomagnetic data suggested were near the equator at the time. The implications were staggering. If glaciers reached sea level at the tropics, the rest of the planet must have been frozen solid. The original hard snowball theory, championed in the late 1990s, proposed a runaway ice albedo feedback loop. The concept is straightforward physics. As ice expands from the poles, it reflects more sunlight back into space. This high albedo cools the Earth further, driving the ice edge closer to the equator. Once the ice crosses a critical latitude, roughly 30 degrees, the cooling becomes self-sustaining. The model suggested the ice sheets would rapidly snap shut at the equator, encasing the entire ocean in that thick shell of ice. In this hard snowball scenario, the hydrological cycle would have virtually stopped. The oceans would be sealed off from the atmosphere, causing oxygen levels in the water to plummet. Life, limited to single-celled organisms and simple algae, would have faced a mass extinction, surviving only in deep-sea hydrothermal vents, or perhaps in tiny pockets of meltwater on the ice surface. But cracks began to appear in this solid ice model. The biological record did not show a mass extinction event consistent with a total global freeze. Furthermore, sedimentary structures requiring open water, such as wave ripples, were found within glacial sequences. This brings us to the definition of the Slushball Earth. The Slushball Earth hypothesis, sometimes referred to as the water belt hypothesis, proposes that while the Earth did experience severe glaciation, it never completely froze over. Instead, a band of open water, perhaps moving seasonally or persisting year-round, remained around the equator. In this scenario, massive ice sheets covered the continents and much of the polar and mid-latitude oceans, but the tropical oceans remained partially open. This distinction changes everything. Because of the open water, the hydrological cycle continued. Evaporation and precipitation persisted, albeit at reduced rates compared to today. This allowed glaciers to be wet-based, meaning they could move and erode rock, rather than being cold-based, frozen to the bedrock and stagnant. Most importantly, the open tropical waters provided a vast refugium for photosynthetic life. Algae and cyanobacteria could continue to harvest sunlight, maintaining oxygen levels in the surface waters, and supporting a food web that would eventually drive the evolution of multicellular animals. The Slushball model essentially argues for a soft freeze, a planetary state that balances on the knife edge between a modern climate and a full snowball, stabilized by feedback loops that prevented the ice from closing the equatorial gap. The primary battlefield for this debate is the geological record. As the saying goes, the rocks don't lie, but they certainly require careful interpretation. Proponents of the Slushball hypothesis point to several specific features in cryogenian rocks that are incredibly difficult to explain with a solid ice cover. First, consider wave ripples and storm deposits. One of the most damning pieces of evidence against a solid ice cover is the presence of wave-formed sedimentary structures within glacial deposits. In the Nantuo Formation of South China and similar deposits in Australia and Death Valley, geologists have identified sandstone beds with symmetrical ripple marks. The physics here are undeniable. Symmetrical ripples are formed by the oscillatory motion of water waves generated by wind. For wind to generate waves that touch the seafloor, there must be open water exposed to the atmosphere. If these rocks were deposited during the height of the glaciation, as the stratigraphy suggests, then the oceans could not have been covered by a thick, stagnant ice shelf. There must have been enough open water for winds to whip up storms and generate swells. Another key geological clue comes from dropstones found in non-glacial varves. Dropstones are large rocks found in fine-grained sediments, interpreted as debris dropped from melting icebergs. In a hard snowball scenario, the ocean surface is a solid ice shelf. Icebergs cannot drift freely and drop stones into open water sediments because there is no open water. However, many cryogenian deposits show dropstones embedded in laminated mudstones, or varves, that show signs of current activity and regular sediment deposition. This implies a drift ice scenario, much like the modern Southern Ocean, where icebergs calve from continental glaciers and float into open seas, melting and dropping their stony cargo as they go. We also have to look at the sheer volume of glacial sediment. A thick, stagnant ice shell would exert little erosional force on the continents because the hydrological cycle, specifically snowfall, would be minimal. However, the cryogenian rock record contains massive volumes of glacial sediment known as diamictites. A slushball Earth with its functioning hydrological cycle would support vigorous evaporation from the open tropical oceans. This moisture would fall as heavy snow on the continents, feeding active, flowing glaciers that ground down mountains and transported vast amounts of sediment to the oceans. The sheer volume of cryogenian glacial rock supports the idea of a wet and dynamic ice age, not a dry and static one. While the geology provides the physical framework, perhaps the most compelling argument for the slushball hypothesis comes from biology. If the Earth had truly frozen over completely for millions of years, the consequences for life should have been catastrophic. Yet the fossil record tells a different story. Photosynthetic organisms require sunlight. In a hard snowball scenario, the ice cover is estimated to be hundreds of meters to a kilometer thick. While some light might penetrate thin ice, a kilometer of ice would plunge the ocean into absolute darkness. However, analysis of biomarkers and black shales from the Cryogenian reveals that eukaryotic algae, specifically benthic phototrophic macroalgae, not only survived but thrived during this period. For example, in 2023, researchers working in the Shenongjia Forestry District in China discovered fossils of multicellular algae in black shales dating to the Marinoan glaciation. These organisms lived on the sea floor in shallow waters. Their preservation implies that sunlight was reaching the bottom of the sea, which is impossible under a thick ice shelf but perfectly consistent with the open waters of a slushball Earth. Furthermore, the geological record shows no evidence of a mass extinction event corresponding to the onset of the Snowball Earth. The diversity of acritarchs remains relatively stable across the glacial intervals. A hard freeze should have wiped out the vast majority of surface-dwelling life, leaving a distinct dead zone in the fossil record. The absence of such a gap suggests that widespread refugia, like the tropical open ocean of the slushball model, allowed lineages to persist uninterrupted. Even more fascinating is the idea that the cryogenian glaciations were not just a hurdle for life to survive, but the very driver of complex life. Recent research has suggested that the slushball state might have been the crucible that forged the first animals. This involves something called the viscosity trap. A colder ocean is more viscous, meaning it is thicker. For microscopic single-celled organisms that rely on diffusion or simple flagella to move and feed, a viscous ocean is a nightmare. It creates a starvation trap where nutrients don't diffuse fast enough. Models show that one way to overcome this physical constraint is to get bigger. Larger organisms can move more efficiently through viscous fluids and access more nutrient flow. The slushball Earth provided a unique environment: cold, viscous oceans with limited but available nutrients in open water zones. This selective pressure may have forced single-celled eukaryotes to aggregate or evolve larger multicellular forms to survive. Thus, the slushball state might have been the catalyst for the evolution of multicellularity, setting the stage for the Ediacaran biota and the subsequent Cambrian explosion. Now, let us turn to the climate modeling. For years, climate modelers struggled to create a stable slushball. Simple models tended to be bistable, meaning the Earth was either warm or fully frozen. Once the ice passed 30 degrees latitude, the albedo feedback was assumed to be unstoppable. However, newer, more sophisticated models have identified a stable intermediate state, often referred to as the Jormungen state, named after the North sea serpent that encircles the world. These models incorporate the dynamics of sea ice. Early models treated sea ice as a static white sheet, but real sea ice flows, cracks, and exposes dark water. When models incorporate wind-driven ice dynamics, the strong tropical trade winds push sea ice away from the equator. This mechanical force works against the freezing temperature, constantly opening up polynyas, or areas of open water, in the tropics. These models show that a stable waterbelt of open ocean can exist even when global temperatures are freezing. This belt acts as a thermostat, absorbing enough solar radiation to prevent the ice sheets from closing, even as the rest of the planet remains in a deep freeze. This also solves the so-called exit problem. One of the biggest criticisms of the hard snowball theory is how you get out of it. To melt a fully frozen Earth, volcanic carbon dioxide would need to build up to incredibly high levels, perhaps 350 times modern levels, to overcome the high albedo of the ice. This would result in an instant super greenhouse or hothouse Earth the moment the ice melted, cooking the planet. A slushball Earth has a lower albedo than a snowball because of the dark open water. Therefore, it requires less carbon dioxide to deglaciate. This aligns better with proxy records of cryogenian CO2, which, while high, do not always show the extreme spikes required by the hard snowball termination. The transition from slushball to a warm interglacial is a smoother, more plausible climatic shift. Despite the mounting evidence, the debate remains active. Proponents of the hard snowball argue that massive limestone layers called cap carbonates, which sit directly on top of glacial deposits, are best explained by the rapid meltdown of a hard snowball and the resulting acid rain. They also point to the synchronicity of the glaciations globally. However, slushball proponents counter that cap carbonates can form via the mixing of alkalinity-rich deep waters with surface waters during a deglaciation, without requiring a super greenhouse atmosphere. They also argue that the energy required to freeze the tropical ocean to a kilometer depth is staggering, and that the latent heat of the ocean, combined with wind and currents, makes a 100% freeze nearly impossible to achieve in realistic circulation models. In conclusion, the debate between snowball and slushball is more than just geological pedantry. It is the origin story of complex life on Earth. If the Earth was a hard snowball, then life is incredibly resilient, surviving in the most extreme bottleneck imaginable. But if the Earth was a slushball, then the glaciations were not a suppressor but an incubator. The open tropical belt was a crucible, where intense competition, isolation, and unique physical pressures like ocean viscosity forced life to innovate. Current evidence, from the wave ripples in the rocks to the survival of algae and the physics of sea ice, heavily favors the slushball scenario. It paints a portrait of a cryogenian Earth that was hostile but habitable. In the slushy, sun-dappled waters of the cryogenian equator, amidst bobbing icebergs and howling winds, the first ancestors of all animals may have swum. The slushball was not the end of the world. It was the beginning of ours.